Hi, so hello everyone. Thank you for joining my presentation. I see that there are still some people joining up there, and the door is now closed, so I can start it, I guess. So, my name is Cesar, and today I'm here presenting Java in space, and I'll talk about what I did during my PhD research, which I developed at the European Space Agency, together with TU Graz. So this was my university. TU Graz is in Austria, but I spend most of my time in ESOC. ESOC is in Darmstadt, which is close to Frankfurt in Germany. So I would like to start with a question to the public. And the first question is, which one is more powerful? So to you, what do you think? An off-the-shelf processor from electronics shop or a space processor? So please put your hand in the air if you think that a processor that you can buy in an electronics shop, please put your hand in the air if you think this one is more powerful. Okay, that's good. So you got it right. What happens is that space processors need to be radiation hardened, and there are a battery of tests that they need to go through before they can be used in space. So there's something called 10 years lag, which basically says that the radiation hardened processors lag 10 years behind commercial processors that any single one of you can buy it. What about software? In space, we're still using monolithic architectures, so everything is very monolithic, and there's still little reuse. And in Europe, we already do something called POS tailoring, where basically we have a standard, and usually we can pick up this standard that already exists, and here we can do some reusing, but usually you tailor this standard to suit your mission. But if you go, for example, to the US, many of their missions are, they do it actually from scratch every single time. So, what is the European Space Agency doing to try to push forward into new ideas and new software? They want to launch the OPSAT mission. So the launch is expected to be done in 2019. And OPSAT is a Nano Satellite mission with the objective of breaking the never flown will not fly cycle in the area of mission operations. So experimenters can make their own software experiments, and they can send it to space. This is the idea of OPSAT. So we have identified about 100 experiments, and these ones can be run in OPSAT because there we have vast amount of storage, 16 gigabyte, high processing power, ARM v7, and it's even capable of running a full operating system and Java. That's why we're here. So this is OPSAT. It's, as I told you before, it's a nano satellite. It's about this size, so it's quite small. Usually normal satellites are the size of a car or a bus, so in that scale. And when you compare it to nano satellite with those big satellites, they're much smaller. But they're actually quite powerful, so you can still take pictures, and you can put, for example, in this case, what the OPSAT mission is doing is to put a very advanced onboard processor compared to what we use today, and to try new software and to try to push forward into new ideas. Okay, now I'm going to tell you a little bit about the MO architecture. The CCSDS, you can think of it as the IEEE for space. So CCSDS stands for the Consultative Committee for Space Data Systems. And what they're doing there right now is to define service-oriented architecture, which is called DMO architecture. And one of the advantages is that this framework or this architecture is agnostic from the transport, so we can actually switch this last layer with TCP/IP or space packets, which is actually what we use in space, and or any other transport. And this allows us, for example, to do tests on ground in a much easier and faster way than in previous days. Now, what did I do during my research at ESA? What I did there was to use the MO architecture and build on top of it. So that's how I came up with the NanoSatmo Framework. It is a software framework for nanosatellites based on CCSDS mission operations services. So what are the new characteristics and new concepts? Basically, we bring apps into space, just like as in your phone, where you can install them, start, stop. So we have this ability to do software management. There's also monitoring and control capabilities for these apps. So we can, we have different services like alert service or parameter service or action service where we can interact with it. The NanoSatmo Framework is also platform independent. This means that these apps are portable and you can use them in different nanosatellites. And finally, it is open source. So what I did was to guarantee that all the software that I developed during my research is available online on GitHub. So any single one of you can go on GitHub and download it. Okay, so usually I use the smartphones analogy because it's the easier and faster way for anyone to understand what I'm actually talking about. And just as in a smartphone where you have your apps on the left side and then you have iOS or Android sitting in between your actual platform, and this allows you basically to switch between a Samsung phone or an LG phone, and you can change the platform, but your app remains the same, thanks to this layer that you have in between. So the same idea can be applied to nanosatellites, and you can have nanosatellite A or OPSAT, and you can have your apps there, and between you have the NanoSatmo Framework. Okay? So in the NanoSatmo Framework, we have different problem domains. So what I managed to do during my research was to completely decouple these domains. And the beauty of this is that when someone on ground is developing a software application, they are decoupled from the other part of the development. So they don't need to be working together so closely, thanks to using standards and to having this modular approach. As I was telling you, this modular approach, I defined something called NMF composites. And these composites are a set of pre-developed components that are ready to be used. So think of them as like Lego bricks, where you can just go to the framework, grab them, hook them into your software, and you can start you can start the plug-and-play interaction between these different segments. Now, I'm going to present a demo in a couple of slides. So I need to introduce what is the NanoSatmo Supervisor. So this is one of the components. And basically, this is the one that is on the onboard computer flying in space. And in the NMF world, the NanoSatmo Supervisor is responsible for start, stop, and killing these apps. It's also responsible for installing, uninstalling, and updating these packages. And you can also, it allows you to discover your apps that are currently running. So I'll show you a demo where we can see the NanoSatmo Supervisor initiating these apps. Okay, so in the demo, what you are going to see next is, okay, my pointer. So we have CTT, which is a GUI. It's hooked into the ground MO adapter, which is one of these components. One of these components from the NMF composites. We're going to connect to the NanoSatmo Supervisor. Then what we're going to do is to instantiate one app. Then we're going to stop it. And then we're going to start again app A and then app B. Okay? So this is the consumer test tool. The supervisor is running on the background. I'm connecting to the supervisor using this CTT. Now this is my apps launcher service. I'm going to select one of the apps, and I'm pressing run. Now this app is starting. Now we're going to see some output from the app. And we can find it on the directory service. We can see it there. We can select it. And now what we're going to do is to connect to this app. And we can see that this app has a set of parameters. This is very simple. Basically, it's just a clock that every second it just pushes the seconds component. So it's a very simple demo app. Now I'm stopping it. So we're going to see that on top there, the provider status is going to change to unresponsive. And the parameters are no longer being received, as you can see. And you can no longer find this app on the directory service, so it's gone. Now what I'm going to do is to instantiate two apps, and you'll see them running in parallel. So I started the first one. It's starting. It started. You can find it on the directory service. You can select it. You can connect to it. You can see that it's alive once again. Everything is working fine. Now I'm going to select the second one. I'm going to press run. It started. And now I can find it once again on the directory service. I can see my two apps over there. I can connect to my second app, and we can see that we have some actions defined over there. And it's alive, the provider status. Okay, this was the demo. Now, as part of my research, I also did a software development kit. And this software development kit includes source code demos, both for ground and also for space. So you can see how to make these apps on your own. The consumer test tool is also available there. So the tool that you just have seen it being used. Then there's a playground environment where you can put your apps and try them, just as I've done it during the demo. There's also an NMF package assembler, which allows you to assemble packages that you can send to space and then install your apps. And of course, finally, some documentation. So, the lifecycle of an NMF app, the idea behind is that anyone can download the NMF software development kit, just as I explained you before. It's available online. You can develop and debug your NMF app. Then once you're happy with what you have, you can create your NMF package. Then you can test it before sending it to space. You can test it on a simulator. I'm going to show you on the next slide what our simulator looks like in ESA. You can test it on the simulator. If you're not happy with the results, you can go back, of course, to the develop/debug NMF app stage. And once you're happy with it, you can finally transfer it to your Nano Satellite and install and run it on your Nano Satellite. So, a quick introduction about what is a Flatset. A Flatset is a spacecraft model that allows functional verification and validation. So basically, this is what I built while I was at ESA. And these CubeSats and these Nano Satellites usually follow this CubeSat standard, which they have like these boards this size and like this size. And basically, you can stack them on top of each other, and that's how you have this form of these cubes. So what we actually have here on our Flatset is a flat surface where we can plug these boards parallel to each other. So we have a bus that runs on that on this red surface here. So I used this Flatset to try out the NanoSatmo Framework, and the code was actually running on these two boards, or actually on one of them. And what this allows us to do is to try the software in a very similar environment to the actual Nano Satellite. So this was like my test bed. Okay. So how is it to be working at the European Space Agency? So as I told you before, I did this research in collaboration with the European Space Agency and TU Graz under the Network Partnering Initiative, or NPI program. And basically, it's an international environment. So we have many different people there from different countries. So I'm actually Portuguese, and I was living in Germany, but there are many other nations: Spanish people, French, Italian, etc., etc. So this, of course, brings many different cultures together. So we have to learn to live together in this multicultural environment where you have not only an espresso coffee machine, but also a normal coffee that other people drink. And of course, it was awesome. I really enjoyed my time there. So, yeah. So that's it for my presentation. I would like to thank you. This was the NanoSatmo Framework, Java in Space. And I want to spend a few minutes just talking about what's next. So currently, I'm no longer at the European Space Agency. I'm working on my own, and I'm developing something called Astro Missions, and it's a satellite simulator with many exciting missions. This is for younger people, and my objective is to make them want and inspire the next generation of young people to become space scientists and engineers. So that's my objective with Astro Missions. And of course, you can download the demo. It's beta at the moment, so it's still not finalized. It's available at astromissions.com. And yeah, this is the end of my presentation. So thank you. Maybe we open up for questions.
So thank you, and we have a lot of questions. So we have a lot of time. So I'm sure you will be able to answer on it. So the first one: can you buy a processing time on NanoSat? Just like can deploy something to NanoSat and try it in real space. It's just...
Can you say it again?
Yeah, processing time. So like
processing time.
Yeah, like using cloud like AWS or Google Cloud. Can you deploy your own and buy
You mean
time?
like a satellite as a service?
Yes.
At the moment, no, but that's a possibility, yes. Currently, no one is doing it, but in theory, actually, that would be actually, I'm not sure if... yeah, that's coming from the public, not from you.
Yes,
or,
yes.
Okay. Because actually, I wrote that on my dissertation. That's why I was wondering. So yes, that's one possibility. So basically, you could give this software framework to people. Anyone can download it, make their own app. And if you have the concept of satellite as a service, where anyone can send it to space and actually deploy it there, if you have a safe environment, just like as you were saying, yeah, in theory it's possible, but at the moment nobody is doing it.
Okay, fair
Yet.
enough. And can apps in NanoSat use any sensors? And I can add, what type of software will be useful to run on this NanoSat? What you can get from sensors and so on.
Okay, so in OPSAT, I can go back to this slide. So in OPSAT, we actually have the instruments that we have we have a camera. There's actually a company called Planet Labs. I'm not sure if people are familiar with. It's an American company, and they actually want to launch a constellation of nanosatellites, actually with the exact same size as this one. And when we're talking about these big constellations, we're talking about like 700 of them. So, and hundreds of it. And what you can actually do, or their objective is to map the Earth every single day. So they want to take pictures of ground, and so you can see the evolution of a certain area of what's happening every single day. So that this is their big objective. To answer what are the other instruments that we have in OPSAT, we also have optical radio, so we want to do some laser testing with this satellite. And yeah, that's it. Next question.
And we are on Java conference, and the question is, why Java? Why do you use Java?
So actually, there was no specific reason why I picked Java. The reason behind is that there was already a lot of software for the CCSDS mission operation services developed in Java. So instead of me going through again to try to develop every single layer, I had the starting point. So that's why I picked Java, because it was available. We had the technical knowledge in ESA, so it was much faster to pick it and start it from there.
Okay, and one interesting question about, is there any way to start your own NanoSat? Like someone from this audience can start their own. Any costs? How much it will cost to start your own NanoSat?
To launch? Or
to launch, yes.
If you have $500,000, I think you can do it.
That's fair enough. It's okay. We are Java developers, so we can do it.
But I would suggest to go with 2 million, so you have a margin.
Okay.
Yeah?
So
$500,000, it's tight. Okay.
Okay. Not for senior developers, but team leads can. Okay. Okay. Fair enough. And interesting question about Docker. You know, can you use Docker in space to abstract everything?
Actually, yeah, that was one of the ideas of OPSAT. One of the experiments is to use Docker in space. So this has been proposed already. And in 2019, when OPSAT is launched, hopefully we'll try Docker there. So yes.
Okay, cool. And how we can break the satellite?
How you can break?
Yes, using Java, of course. So, this is a piece of software that can fail. And you write in the tests and run in simulator, but how you protect from failures?
Yeah. So I didn't tell you about this, but OPSAT is actually, it doesn't only have one onboard computer, it actually has two. So the first one is actually, if you can see it, is like here. It's called NanoMind. And this is actually not an ARM processor and super fast like the experimental platform. And what we actually have is like 2 satellites inside one. So the experimental platform is actually where you're going to try these new software experiments, but we have this one behind. So if something fails, we just turn the other off. We say, no more experiments. Okay. Sorry, buddy. We're going to shut you down, and then we can always repatch the software. So that's how you do the protection mechanism.
Okay, cool. Maybe Docker will help as well. And what protocol do you use to communicate with the satellite? Maybe like TCP, UDP, and so on. Yeah,
so in space you don't actually use TCP, or actually there were some people trying it because that's quite an interesting thing to have, but what you actually use is space packets, and there's a whole different layering into it. So you have these frames that are transported from, okay, so you have something called MOC, which is the Mission Operations Center. Then this is where you issue your telecommands, and these telecommands need to be transported to the ground station, and then the ground station is actually where you send the telecommands to your spacecraft. So
this protocol is open, right? Or
the SPP, space packets, yes. So the space packet protocol is available online. It's made by the CCSDS, as I told you before. And this is actually what you do, what you send to space. Now, there were some people trying TCP/IP because it's an obvious thing to think about when you're thinking in terms of communications. And there are some problems, so you need to do some adjustments because of lag, etc., etc. There are many things. It's not that simple. You can encapsulate TCP/IP inside these space packets, but it starts becoming too messy, too crowded.
Okay,
so it's not efficient.
That's the next question. Are like trade-offs or limitations of this protocol? So.
Trade-offs against what?
Against using this protocol to deliver software or to communicate with the NanoSat. I mean, is there any limitations to use this special protocol?
Space packet protocol? Yeah. No, but it's just better because it doesn't have as much data as the TCP/IP, so it's smaller. Mm-hmm. Recently, they are also trying, this might sound silly to you, but because file transfer is something that you all are familiar with, FTP, but in space, this is something new. And it's called CFDP, so CCSDS, File Delivery Protocol, and this is one of the big things in space that has been done for the past 5-10 years, and now people are starting to use CFDP in space. So basically, when you have big amounts of data that you want to downlink, instead of just bombarding with telemetry with these parameters, what you can actually do is you store them in the spacecraft, you compress, and then you send this, you do the file transfer. So Yeah.
Okay. So the last question, and I think it's the most important one. Can you communicate from space with the world? I mean, can I tweet from NanoSat?
Can you what?
Can I tweet? Use Twitter?
Tweet.
Yes, from NanoSat. Can I communicate with the world?
In theory, yes. I mean, if you have a communication link, you can do it.
But is there any communication link from NanoSat to the world? So I can write software that will doing a post in my Twitter.
Actually, when I was
you did it, yes.
When I was developing the NanoSatmo Framework, I got to a point where I managed to establish I was able to start apps, and I wanted to try something different. So what I actually did was to make a Facebook post from the app. That was very interesting because it actually follows the chain. So I was not talking directly with Facebook, but it was going to the ground application, and then the ground application would actually talk with Facebook to make the post. Mm-hmm. So that was actually pretty interesting, and yeah. So I guess if you have an API for Twitter, you can plug it into your ground components and do it, yes. So that's an interesting experiment. You can submit it to Upset, and you can probably code it in, you guys are experts, so I guess I would say in less than 1 week.
Awesome, awesome. So thank you very much for Java in Space, and maybe see you next year. Okay, thank you guys.
Thank you.